Good morning and welcome to Tech 259 on Monday, February 15th. Today we're going to talk in some more detail about our second mode of heat transfer, which is convection heat transfer. But before we do that, let's review problem set number 8, which was our problem set about conduction heat transfer. So I'm going to share my screen. Here we go. All right, so here is problem set number 8 about conduction heat transfer. And it says that we're thinking about adding another layer of insulation to the walls of our house. The existing wall has a layer of brick with this thermal conductivity that's 15 centimeters thick, and then that's in series with an interior layer of plaster with this thermal conductivity that's 2 centimeters thick. And we're thinking about adding a 2 centimeter thick layer of foam that has this thermal conductivity to the entire wall area. And we add up all the surface area of our home and we calculate that it is 150 meters squared. And we're going to say the outside temperature is 0 degrees Celsius, which has been actually a little higher than it's been in central Illinois recently for the better part of the last week. And the inside temperature is 24 degrees Celsius. So making these assumptions about, say, the average temperatures inside and outside, we want to find the heat loss in watts to the outside air before we add insulation. So how much heat is being transferred from the inside air to the outside air in joules per second, which is watts. And then part B is what's the heat loss in watts to the outside air after adding insulation. So we think about our thermal resistance network, and we'll do part A first. So that's before adding any insulation. So before we add any insulation, there's only two thermal resistances. One is for the brick and one is for the plaster inside. Right? So we have our equation for the thermal resistance of a planar wall, and that's given here on page 17. It's L divided by Ka, where L is the thickness of that layer, K is the thermal conductivity, and A is the surface area that the heat is passing through. So we've got two thermal resistances that are in series. We know they're in series because the heat has to pass through both of them. It doesn't have a choice to pass through one or the other. The heat has to pass through both layers. In the same way that if you have electrical components in series, the current has to pass through both of those components. It doesn't have a choice. All right, so here we know that we've got these in series. So the heat has to pass through this thermal resistance, and then it has to pass through this thermal resistance. And we know that for components in series, whether we're talking about electrical components or thermal components, to get the total resistance, we just add the components that are in series. So we'll call this L1 divided by K1A1. That's going to be for the brick. And we'll call this L2 divided by K2A2. That's going to be for the plaster. So now we just have to put in our known parameters that are given to us. And it tells us the thickness, that's L. Thickness of the brick is 0.15 meters, which is 15 centimeters. And the thermal conductivity of the brick is 0.72 watts per meter per degree Celsius. And the area of the brick, which is going to be the same as the area of the plaster, the total surface area is 150 meters squared. So that's for resistance 1. And now we add resistance 2. Plug in numbers. L2 is the thickness of the plaster. We were told it was 2 centimeters, which is 0.02 meters. You want to put this in meters so that it will cancel out with these meters units down here. If you don't, then you'll have centimeters, and you won't be able to cancel those out. So once again, this is showing why it's important to keep your meters, keep your units in your problems. In this case, keep the meters in here so that you'll know when you can cancel these out. All right, here also, meters, and we have meters squared, and we have meters down here. So clearly we have to use the units of meters for length in this problem. All right, so so it told us it was 2 centimeters, which is the same as 0.02 meters. And then the thermal conductivity of the plaster was given as 0.22 watts per meter per degree Celsius. And once again, the total surface area that the heat is passing through is 150 meters squared. So that's A2. All right, so now that we've kept our units, we can look at how these units are going to cancel out or not. And we see that we have meters up here in the numerator. We have meters squared in the denominator. And we also have meters in the denominator of the denominator. And when we have a unit in the denominator of the denominator, then we can actually say it's in the numerator, because if you're dividing by something that has a unit in the denominator, then actually you can bring it up to the numerator. Example that's probably the easiest to think about is 1 divided by 1/2. So how many times does half go into 1? 2, right? Twice. So really that 2 that's in the denominator of the denominator is actually in the numerator. So that's a rule of algebra. If something is in the denominator of the denominator, like you have a fraction in the denominator, then the denominator of the denominator is in the numerator. That's tricky to say. That's a bit of a tongue twister, but it works. So we actually have this meter up here in the numerator. So actually we have meters squared up here in the numerator, and we have meters squared in the denominator. Or you know what? There's another way to think about this too. This units of meters cancels out with one of these. This is meters squared. So that cancels out one of these. And then here we have meters in the denominator of the denominator, and that cancels out the other one of these. So either way you think about it, the meters units are getting canceled out here. Same thing over here. Our meters cancel out, and we're left with watts per degree Celsius in the denominator. But note that degrees Celsius is in the denominator of the denominator, and so really it's up here in the numerator. All right, so you plug all these numbers into your calculator, and what you get for a final result is 0.0020, and the units here are degrees Celsius per watt. Why? Because degrees Celsius here is in the denominator of the denominator, and watts is just in the denominator. So degrees Celsius comes up to the numerator, and we can say that's degrees Celsius per watt. All right, so that is our total thermal resistance for this part of the problem. So now we can plug that in to our equation for conduction heat transfer. And now the rest is pretty easy, because now we can just put that into our total, and we have T1 and we have T2. So plug all those numbers in. 0 degrees minus 24 degrees Celsius divided by our thermal resistance. And now you can see that degrees Celsius cancels out, and watts is in the denominator of the denominator, so it's actually up here in the numerator. All right, so when you do this calculation on your calculator, you get about negative 12,000 watts, which is negative 12 kilowatts. All right. Why is there a negative sign right there? Well, it's because we took 0 minus 24. And the reason we did that is because we defined T1 as being the outside temperature and T2 as being the inside temperature. So in our diagram right here, we always assumed that we're having heat transfer from left to right. So we assumed that we were having heat transfer from left to right, T1 to T2, but actually it's not left to right. It's always from hot to cold. So actually our heat transfer is a negative, which means that it's going from right to left. If we would have defined the left side over here as being our inside, like at 24 degrees Celsius, and we would have defined over here on the right as being our outside at 0 degrees Celsius, we would have got a positive number because we would have had 24 degrees Celsius minus 0 degrees Celsius. But it doesn't really matter as long as you understand that this amount of heat, 12 kilowatts, is being transferred from the inside at higher temperature to the outside at lower temperature. As long as you understand that, it doesn't really matter which way we define our T1 and our T2, which one is which. All right, so we got negative 12 kilowatts of heat transfer, and that is heat transfer from the house to the outside. Now, in part B, it says, what if we added a layer of insulation? So if we add that insulation around the entire exterior wall of the house, we just have another thermal resistance, and it's in series. So now the heat has to go through not just the brick and the plaster, but also the insulation. And it doesn't really matter which order, as long as they're in series like this, it doesn't matter which order you put these in. It's going to have to go through all three of them anyway. So same situation as up here. We just add our insulation to the end of it as well. So now we have not just R1 and R2, but we also have R3 for the insulation. So here's what our total thermal resistance is going to be. So we already did this part up here and we found this number. So let's not redo that. I'm just going to put that in here. So this number comes from up here because it's the exact same as what we calculated up here for the brick and the plaster. So we have 0.0020 degrees Celsius per watt for the brick and plaster in series. And now we also have the insulation. So here is our thickness of our insulation. It's 2 centimeters, which is 0.02 meters. And our thermal conductivity of the insulation is 0.026 watts per meter per degree Celsius. And the surface area is 150 meters squared once again. And once again, our meters cancel out. So we're going to be left with watts per degree Celsius in the denominator, which means that our units are degrees Celsius per watt. So we plug this into the calculator and we get a total of 0.0071 degrees Celsius per watt. That's our new total thermal resistance. So we plug that into our conduction equation. And we plug in T1 and T2. And these are the numbers we get. Once again, we defined T1 to be 0 degrees Celsius. That's the way I did it anyway. And we defined T2 to be 24 degrees Celsius. So we're going to get a negative number again, which just means that we're actually having heat transferred from right to left instead of left to right. So that's what our numbers look like. And we get negative 3,367 watts, or negative 3.37 kilowatts, which is heat transferred, once again, from the inside of the house at 24 degrees Celsius to the outside of the house at 0 degrees Celsius. So look at the big difference that adding that insulation made. That made a huge difference. It was only 2 centimeters. It's like that much of insulation, but that made a huge difference in the amount of heat lost from the house. So where would all that heat be coming from if I didn't have the insulation? Well, we'd be losing that much heat. So we'd have to make up for that with the furnace. So our furnace in this case would have to come up with a lot more heat. It'd have to produce a lot more heat in order to make up for all that heat that was being lost to the outside. You add a bunch of insulation, or actually even not that much insulation, but you add some insulation to the whole house, and now your furnace doesn't have to work nearly as hard. It doesn't have to produce nearly as much heat. So that's a much more efficient system where you don't have to produce as much heat. Your furnace doesn't have to burn as much fuel to heat the house. So this is a good example of thermal efficiency of homes. Okay, problem number 2 says that we have a biomass-fired electricity generation plant. So we are going to produce steam from combusting biomass, like wood, some type of wood-type fuel. And it's got a steam pipe from the boiler to the turbine, and we're given the dimensions of the pipe, and it's wrapped in a layer of insulation outside of that pipe. And it says the temperature of the steam inside is 200 degrees Celsius, and the pipe's exterior temperature outside the insulation is 30 degrees Celsius. The length of the pipe is 20 meters, and we want to calculate the heat loss from the pipe if we're given the thermal conductivity of the steel and the insulation. So here's a cross section of our pipe, and we're given the internal radius of the steel pipe and the external radius of the steel pipe, which is also the internal radius of the insulation, and we're given the external radius of the insulation. All right, and we're given the temperatures inside here and outside here and the thermal conductivities, and we want to calculate the heat loss. All right, so this is really quite similar to the previous problem. Any heat that is going from the inside to the outside is going to have to pass through both the steel and the insulation. So what does that tell us about the thermal resistance network? It tells us they're in series because the heat loss has to go through both of these. It doesn't have a choice about which one to go through. It has to go through both. So they're in series. So we're going to have thermal resistances in series. But this time it's slightly different because these are circles. They're going to be cylinders. And so we have to use the equation for heat loss through a cylinder. So here's our thermal resistance network. We have T1, which I've defined as the inside of the pipe, and T2 is the outside of the pipe at 30 degrees Celsius. Here's resistance number 1 for the steel. Here's resistance number 2 for the insulation. And we're given the thermal resistance for a cylinder on page 17 right here, where R2 is the outside diameter, R1 is the inside diameter, L is the length of the cylinder, and K is the thermal conductivity. So let's plug those in. So here's our general equation for thermal resistance through a cylinder. So here's our equation. R2 is the outside radius of the steel pipe. R1 is the inside radius of the steel pipe. L is the length of the pipe. K is the thermal conductivity of the steel here for resistance 1. And then in our second resistance, we have R3, which is our external radius of the insulation, and R2, which is the internal radius of the insulation. All right, and then L is going to be the same, and then K is going to be the thermal conductivity of the insulation. So plug those values in, keeping your units, and your meters are going to cancel out here in the numerator, and then down here, they're going to cancel out here from L and here from K. So once again, all of our meters cancel out, and we're going to be left with watts per degree Celsius, both in the denominator. So once again, our units are going to end up being degrees Celsius per watt because we have degrees Celsius in the denominator of the denominator. All right, so you plug these into your calculator and you get this value, very, very small value, for the thermal resistance of the steel pipe. And you get this value, 0.0684, for the thermal resistance through the insulation layer on the outside of the pipe. So compare these two numbers just for fun and notice that the thermal resistance of the insulation is much, much greater, like several orders of magnitude, like 100 or 1,000 times greater than the thermal resistance of the steel pipe, which makes sense. I mean, there's going to be a lot, it's a lot easier for heat to transfer through a steel pipe than it is for the heat to transfer through the insulation. That's kind of the whole point of putting the insulation on it, right? All right, so we add these up because they're in series. And our final answer for the thermal resistance here, total, is 0.0684. So notice that this resistance here is pretty much negligible compared to the resistance right here. So this is our total thermal resistance. So we plug that into our conduction heat transfer equation. So here's T1, here's T2. Notice here, it doesn't matter if you put it in Celsius or Kelvin because the delta T, the difference in temperature, would be the same, whether it's in Celsius or Kelvin here. So it doesn't actually matter here whether it's in Celsius or Kelvin. So I just left it in Celsius, and we plug in our thermal resistance there for conduction, and then we plug that into our calculator, and that's what we get, 2,485 watts, which is 2.49 kilowatts. And notice it's a positive number, so that means the heat was transferring left to right, as we assumed, through the thermal resistance network. So the heat is being transferred from the steam to the outside of the pipe, just as you would probably expect or assume. All right, so let me know if you have any questions on conduction heat transfer. It's important that you understand conduction heat transfer because we're going to use some of those same principles, the idea of a thermal resistance network, the analogy to electrical circuits. We're going to use that over and over again in convection and radiation and in combined modes of heat transfer in another week or two. So make sure you get that all cleared up and make sure you understand that. If you don't, I'd be happy to help you understand that. So just let me know. Shoot me an email or come to office hours or ask me after class. All right, so I'm going to end this video here, and in the next video, we'll start talking about convection. I'll see you there.